The screen is visible.
Yes. Madam, you may please start.
Now the screen is visible.
Yeah.
Ma'am, shall we start? Good evening, everyone. I trust you are all doing well and ready for an engaging session. I'm delighted to extend a warm welcome to each and every one of you on behalf of IEEE Education Society Kerala chapter. Today marks the beginning of our talk series, Pro Talks, where seasoned professionals provide insightful talks about their respective fields. We have the privilege of hosting a session on Launch Vehicle Mission Design Challenges by Dr. S. Geetha, who brings with her a wealth of experience and expertise as the Director of Control Systems at Skyroot Aerospace Private Limited, an outstanding scientist and former Program Director of Space Transportation Systems at VSSC ISRO. The domain of space exploration is not only captivating but also fraught with numerous challenges. Launch vehicle mission design requires intensive preparation, creative thinking, and a deep grasp of many technical facets. Dr. S. Geetha will be sharing insights into some of the key challenges encountered in this field, drawing from her extensive experience and expertise. To commence our session, I would like to invite Dr. Geetha Paul, the chair of IEEE Education Society Kerala chapter, to deliver the welcoming address. Ma'am, please proceed with your welcoming address.
Respected Geetha and Dr. Geetha Madam, Vice Chair Bindu Madam, and Advisor Keshwasamy Sir, and all professional members and participants. With great pleasure, I welcome you all to this webinar on vehicle launch and design, organized by IEEE Education Society Kerala chapter. This marked the first professional talk in our series, and I commend the professional team, especially Dr. Bindu and student team, for their initiative in organizing this program. Following the Chandrayaan mission, we are eagerly anticipating acquiring more knowledge, and we trust that this session will be enlightening. On behalf of IEEE Education Society, I extend a warm welcome to Dr. Geetha Madam to this webinar. I also welcome our advisor Keshwasamy Sir, Vice Chair Bindu, and Usha Madam, and all professional and Execo members, and all student members and participants to this webinar. We hope this session will be both informative and engaging. Thank you everyone for your participation and support. Thank you.
Thank you, ma'am. Now, without further ado, let's welcome Dr. S. Geetha to share her expertise with us. Over to you, ma'am.
Okay. Good evening, all of you. And sorry to begin with, because we have lost something like 20-25 minutes. Because some problem maybe with my PC also, I don't know. However, we'll go with the launch vehicle mission design challenges. I have prepared a slide in such a fashion that the challenges what we have faced in the design of autopilot as well as the mission. For PSLE, I have involved in the PSLE, GSLE as well as GSLE Mark 3 RLE, all missions. So we'll go to the next slide, please. Yeah, I have put this like this: mission feasibility and configuration, finalization of launch vehicles and satellites, and then the challenges in the mission design area, and an animated video of rocket launch for Chandrayaan 3. What I am addressing is not related to the Chandrayaan mission. The total launch vehicle, rocket vehicle, launch vehicle mission design only I am addressing. So go to next slide. Yeah. So first of all, the mission feasibility means how do you select the rocket vehicle? Which rocket we have to select? For that, we have to have two requirements. One is the satellite requirements. Satellite, when a satellite comes to you, it is our duty to select which vehicle in the optimal way is applicable for this satellite for this purpose of launching, like what is the orbit, what is the mass, what is the apogee perigee, what is the argument of perigee. All these things are coming from the satellite. Sorry. So multiple space, whether it is a multiple spacecraft mission or a multiple orbit mission or an interplanetary mission or a lunar mission. So based on this, the satellite will have its own payload and the requirements. Then it is the launch vehicle area which decides whether I have to use the present launch vehicle available to us or a new vehicle has to be designed. In that aspect, I have put in the slide, you can see existing launch vehicle or a new launch vehicle. In that, what is the major concern is the satellite mass. So the vehicle mass, satellite mass carrying capacity of the rocket will be varying from vehicle to vehicle. So that is the vehicle configuration. Then we will decide the launch azimuth and the visibility constraints from what are all tracking stations the vehicle is visible, not only in the flying path as well as in the orbit also. And also then the flight safety constraints, loads, what are the loads acting on the vehicle, whether the vehicle is controllable in all phases, and whether the strategy for multiple spacecraft injection is capable, that capability is there for the vehicle or not. For example, in the case of PSLV, we have to have PS4 restart capability. Then only we can have multiple restart option as well as the multiple orbit mission. In one flight itself, we can have multiple satellites, but if you wanted to have different orbits, for example, the first satellite in an orbit of 650, next satellite in an orbit of 850, then we have to raise the orbit. That capability is due to the last fourth stage restart capability. So that is why, with these things into consideration, we'll go to the existing launch vehicle. On the left side, you can see the existing launch vehicles of ISRO: PSLE, GSLE, Mark III, and SSLV. I am telling all these things with respect to the ISRO launch vehicle. On the right side, you can see HLV, which is coming in the new launch vehicle. Reusable launch vehicle is, at present, it is not designed to launch the satellite and all. It is an experiment only, and a recoverable launch vehicle. These are all new launch vehicles. So once this process is over, we will be knowing what is the vehicle, what I have to do. I have to do the design, the following things, whatever I am going to tell for that launch vehicle. So once you are going through this procedure, this itself a great procedure. This we can call it as a mission planning and decision to have which launch vehicle. So once this is over, the launch vehicle and satellite configuration gets finalized. This is one of the challenging area, because suppose the vehicle is big enough, then we will be losing some money because of the cost of the vehicle. For example, for a small satellite, if I am using GSLE or GSLE Mark III, then it won't be cost effective. So cost part and all I am not addressing at all. Next slide. Next slide. So in this slide, I have put on a broad sense what are the mission analysis. The heading alone we will go through. So the mission design consists of many critical activities demanding domain knowledge with powerful computing facilities. So aerodynamic analysis, aerothermal analysis, vehicle data and flight sequencing. Then mission design and analysis, wherein our expertise like trajectory design, guidance design, DAP design, 6D trajectory simulations, all these simulations will come into picture. I will dwell upon that at the later point of the presentation. So I am not telling this here. This is the way we start the design activities. So once this vehicle is finalized, satellite is finalized, then we'll go through the vehicle data. So next slide. So on the feasibility and the configuration selection is over, then to the mission designer, two important points. One is the vehicle data and the next one is the flight sequence. Next slide, please. Next. So this is what is a vehicle data, what it contains. So in terms of bubbles, I have put major thing is the configuration, whatever I have told, whether PSLV, GSLV, PSLV itself, different configurations are there. 6 strap-on configuration, 2 strap-on configuration, 4 strap-on configuration, and 4 alone configuration. So that is the one which you can see on the top configuration. Then the mass properties of the system on the right side you can see, because I cannot show the mouse also. Atmospheric properties, trajectory, navigation and guidance, actuator, launch station. I am going clockwise. Structural data, mass EG properties, propulsion, aerodynamic data. In a nutshell, the vehicle data contains all these information in the baseline 0 version, and subsequent changes which are there, it will go in the next versions. So this document is the one which goes to the mission design. It is a huge document. These are the inputs to that document. Then go to next slide. So then comes the sequence. You know when to ignite, when to cut off, when to separate. All these things are dictated in the launch sequence in a nutshell. So the typical flight events may be ignition, maneuvers, shut off, separations, heat shield separation, cause phases, and the satellite separation. So an optimum sequence of launch events from the first stage ignition till the satellite injection into orbit is called the sequence. So it has to satisfy all mission constraints. Like why I am telling mission constraint is, suppose a visibility is there, then all important stage events like stage ignition, stage separations, stage control of all these things should be visible from the visibility stations. If it is not available from our own visibility stations, then we have to hire also. Suppose there is a cause phase, there is no major events, no visibility is there, then we need not worry about hiring a visibility ground station. Rather than that, we can store the data. That is the important, satisfies all mission constraints. So even though I have put it as ignition, control off and all, visibility is also a major function. And it should ensure smooth functioning of the vehicle for the nominal as well as the off-nominal flight environments. Next slide, please. So that is another point. Launch sequence must satisfy vehicle, ground already told, subsystem requirements which depend on flight environment. Defining the event sequence in real time in onboard is essential to meet all the requirements. That is called RTD. When we started with the ASLV long back, RTD was not there. So after the 2 failures, our study indicated that a real-time decision on board is required. That is why RTD is implemented from the ASLV D3 onwards. So that is a typical strategy, is detecting each critical event on board. That is to take a real-time decision and refer further sequences with respect to the real-time decision until the next RTD is detected. So RTD detection must be highly reliable. What are the constraints? RTD means real-time decision may be based on the sensor data, accelerometer data. So that has to be reliable, and then RTD should not be triggered inadvertently. If an RTD is triggered inadvertently, that also creates problem. And also at the same time, it should meet all the mission safety requirements. Next slide. So this is a typical sequence. I will not dwell upon that. This is to say a typical mission sequence wherein all separations, acceleration based RTD, everything is noted for this 3 stages. Next slide. So launch sequence is a stage transition is a crucial event for the launch sequence. There are 2 crucial requirements of stage transition. Stage transition means when you, as you know, as soon as the function of a stage is over, that will be separated from the ongoing stage. That is to increase the acceleration levels, because an dead mass, if you are carrying, the acceleration will be less. Because of that, the velocity will be less. So the upper stages has to have higher capacity. So that is why we are separating. So in a stage transition, because in the sequence, this is a major event, that first stage to second stage to third stage to fourth stage, it has to be a clean separation. And also at the same time, it has to be the second stage or third stage, wherever it may be, it has to be in the controllable conditions. So the thrust of the spent stage must be slow for the clean separation. Solid motors and liquid engines may have large dispersions in action time. Only after separation of the stage, the next stage can be ignited. So this is the condition for clean separation. And then other one is controlling the spent stages must be off to avoid control induced disturbances. And the large no control zone between the stage transition can cause high rate and error, so that the next stage becomes unable to capture it. So these are conflicting requirements. So that is why an RTD is essential. Next slide. So we have, for a mission designer, the major challenges is you get a vehicle data which is exactly duplicating the vehicle behavior. Next one is the sequence of events satisfying all the constraints with the clean separation and all. Maybe after some two, three trials only, it will be evolving as well as vehicle data as well as the sequence. Even then, for PSLV and all, we are in a stage to say that no further evolvement is required until as changes are there. So for the mission designer, now you have with you the vehicle data as well as the sequence. Then what is the challenge? The challenge is, first of all, the modeling of the vehicle and the satellite. Why? Because on the model only you are working for the design. So the model has to be pakka with respect to the actual vehicle, then only your design will work. That is the first and foremost challenge in the vehicle design, is the modeling of the vehicle with vehicle as well as the satellite. Even though I am telling the vehicle, the satellite is also there. Its properties also governs in the mass inertia properties, flexible properties, everywhere. Then comes the mission aspects like trajectory, navigation, guidance, and control. So each one, below each bubble I have put in the trajectory, it has to be a minimum fuel trajectory. That means it is a optimum fuel. Why optimum means? Whenever you are carrying extra fuel, the mass will be increasing, then the capability has to be increased, then the payload capability will come down. So it has to be done in an optimal fashion. Navigation gives you the present position, altitude, attitude, rate, everything is coming from the navigation. Then why the navigation also is challenging means the accuracy of the orbit insertion or accuracy at any point of the flight time is dictated by the accelerometers or the sensors available. Then actual data, we are working on that data for the feedback control system. So accuracy of the navigation also plays a major role. Accuracy, reliability, and safety of the navigation also plays a major role in the mission design. Then guidance. Guidance is the steering command generation. I am here, I have to go there, with optimal path dictated by the trajectory design. In the presence of off-nominal conditions, off-nominal conditions also, I should reach the desired target condition that is dictated by the guidance. Then the control. Control is the vehicle stability and integrity has to be ensured while following the guidance commands. That is the control. Next slide, please. Next slide, please. Yeah, modeling already I have covered. You can go to the next slide. Then what is the mission design? In the mission design, as I told, the launch vehicle configuration is finalized. Then how to achieve the mission? That is the defined mission in specifications in terms of orbit and orbital dispersions. And the trajectory to be followed with minimum fuel. That is called the trajectory design. How to ensure impact of jettison stages in the safe zone. That is the range safety. and how to ensure safety of the vehicle during atmospheric place. That is the load reduction or wind biasing. So this is the mission design process. Next slide. This is the optimal trajectory design. This whatever figure I have put is for the Mark 3 vehicle. You can see the start point is the launch pad and the end point is the injection point. The optimum fuel for a fixed payload or a maximum payload for a given propellant loading, honoring several constraints. That is called the constraint optimization problem. So here we will be using the point mass trajectory and a trajectory which meets our constraints in terms of visibility, range safety, and the orbital constraints. Then we will assume that this is the trajectory given to you for the guidance design as well as for the autopilot design. Next. So this point, in a nutshell, I have covered earlier itself. Endpoint constraints. Endpoint constraints. What are the endpoint constraints? Like orbit size, inclination, argument of perigee, ascent phase constraints, launch tower clearance, peak dynamic pressure, thermal loads, separation event constraints like dynamic pressure, altitude, impact constraints, tracking constraints. All these things will be considered in the optimal trajectory design. Next slide. So these are the different phases of the trajectory. You can see the first stage, and this is for PSLV, the 4 strap-on separations, 2 strap-on separations. I'm going through in from down to up. Then PS1 separation, PS2 ignition, heat shield separation, PS2 separation, and the CLG phase is the closed loop guidance phase. Next slide. So this is what I have told you, the range safety, because any deviation from the trajectory path with the dispersions allowed to you, if the vehicle is deviating from that path, the safety officer will destruct the vehicle. You can see one destruction happening for the GSLE F06 because of during the heat shield, before the heat shield reacting phase itself, the vehicle has broken. And GSLA F02, because one of the strap-ons didn't ignite, the whole vehicle is destroyed by the safety officer. For that also, destruction mechanism is there in the launch vehicle. So that will be operated. That is only if the vehicle is not functioning properly, it has to be destroyed. So this before the design phase itself, if everything is working also, at any point of time, if the spin stage or the vehicle, because this destruction can happen only up to second stage. So at any point of time, if something happens to the vehicle and if it impacts on the ground, and whether it is the populated area, what is the casualty expectancy, the worldwide, that numbers are there. The impact point casualty expectancy has to be like this. Stage impact point has to be this much nautical miles away from landmass as well as on the uh, ocean. These constraints are given to the mission designer. With that, keeping into consideration only, he'll design the trajectory. You can see the instantaneous impact and all on the graph. So this is also an important point in considering the trajectory. So it has to be optimally designed with the optimum fuel. It has to be designed with maximum conditions like visibility is ensured, all as well as all stage impacts along with the heat shield impact also has to be in the safe zone, and in the presence of any eventuality happening when it is going in flight also, the impact point casualty expectancy has to be within the allowable number, internationally allowable number. Next slide. Next. So once the trajectory is over, then next point is navigation, guidance, and control. Navigation, as I told you, it determines the present state of the vehicle, position, velocity, attitude of the vehicle. Guidance generates the steering commands to reach to you in the desired optimum conditions like orbital conditions. In each stage, there are targets. Suppose I am in the second stage, we will have the second stage target condition. Suppose I am in the third stage target condition. So each way, the guidance design has to be carried out such as to meet the end conditions in that stage. So the control, as I already told, it has to follow the steering commands generated by the guidance. Next slide. So this is like guidance generate the commands. Then navigation gives you information, and then control will give you what is the steering commands, what is the actuator commands in each stage required to meet the steering commands generated by the guidance. Next slide. So this I will skip because this initially itself I told what are the requirements coming from the satellite, whether I am in the low Earth orbit, sun synchronous orbit, geosynchronous orbit. All these things are input to the mission designer initially itself. Based on that only we will be doing the trajectory design as well as the guidance design. Next slide. So in the guidance design, you can have a concern like atmospheric phase is open loop and the exo-atmospheric phase is closed loop. In atmospheric phase, though so many disturbances are there like wind, atmospheric pressure, atmospheric density and all. There we are giving more importance to the clearance of atmosphere without having any problem to the vehicle. So that is why we are putting as the open loop guidance. You can have closed loop guidance also, no issue. But the effectiveness matters in the closed loop guidance. In the sense, it won't be effective because our prime idea is to have clearance of the atmosphere. So in the closed loop guidance, if you are having two orbits, then the orbital maneuvers are required after the first satellite injection. That is why you can see in this orbit, you can have first orbit, circular orbit, second orbit as an elliptical orbit, third is a circular orbit. From the first orbit, by using the satellite fuel, you can go to the second orbit also. But here, first after injecting the first satellite in the first orbit, the rest of the vehicle is reignited to reach to the second orbit and then to the third orbit. So here in this case, there are two satellites, one in orbit number 1 and another one is orbit number 3. Next slide. So this slide, I think this because I have put this slide specifically because later point of time I am telling about the guidance margin. So guidance margin is the one that additional fuel we have kept in each stage to meet the requirements in the eventuality of the performance going off normally. So some additional extra fuel we have to store in each stage. In the usually this additional fuel can be stored in liquid stages only because in the solid stages we cannot store extra fuel. In the liquid stages we have the capability to shut down the stage, keeping some fuel which we can restrict for the off nominal performance of the vehicle. So next slide. Next, okay, this is also a multi-orbit. You can see orbit 1 to orbit 2. You can put the enter button so that will be changing size and inclination alone. So inclination and size of the resultant orbit depend upon the magnitude and the direction of the delta V. Delta V I have shown, the inclination also there. Next slide. Yeah, this is from orbit 2 to orbit 3. Next slide. So all these are coming in the guidance part. So in the case of PSLE C45 mission, we have 3 orbits. First orbit is 748 something. Second orbit 504. Orbit 3 is 485. Orbit 1 is achieved with regular PS4 phase. Then PS4 engine is restarted twice to achieve orbit 2 from orbit 1. And then for the orbit 3, we have used the RCS, that small thrusters, for a long time to reach to orbit 3. So these stars and all, I have put, when you put the enter, it will click. That's why I was telling that I am comfortable with my own way of presentation. Okay, next slide. So coming to the digital autopilot design, as I told you, the guidance will generate the steering commands to you in pitch and yaw direction. Our vehicle, almost all our vehicles are pitch and yaw only steering is there. Roll is no control is there not to roll the vehicle. So there are phases where you have to have rolling also, like spin stabilized vehicle. ASLV last stage is a spin stabilized vehicle. And almost all the satellites, some of the satellites are spin stabilized. Next slide. I think a battery is low is coming from your presentation, I think. Somebody who is presenting, you just see your battery is low. Okay, so this control systems in space law applications, we have two controls. One is satellite control and another one is a launch vehicle control. So the mission requirements for launch vehicle already I have covered. And then analysis methods. The analysis methods depending upon the launch vehicle and satellites will be different. Because as you know, the launch vehicle is a huge structure, whereas satellite is maximum, our satellites contain something like 4,000, less than 4,000 in the case of Chandrayaan 3 also. So the control systems also will be different. And once you are in orbit in the satellite, your control is required only to make it moving in the orbit, no other things. So this slide shows the linear analysis methods that linearize the system and the nonlinear methods. Nonlinearize the system because I thought we our audience being IEEE students. So that is why I have put some slides like this. Control system analysis methods, linear analysis methods. We have to have frequency domain analysis as well as the time domain analysis. And the nonlinear analysis methods includes describing function, phase plane analysis, Lyapunov stability analysis, and Popov stability analysis. So once we are doing the design, all these methods we are using for the design aspects and to get the numbers on board. So simulating the system with all nonlinearities is the best way of nonlinear system analysis. So next slide. So this is the function of the autopilot. What is the function of the autopilot is the DAP being the innermost loop of the navigation, guidance and control. Steer the vehicle along the desired trajectory, maintaining the structural integrity, and controls the altitude of the vehicle in pitch, yaw and roll channels from liftoff to satellite injection, and ensures the stabilization of the attitude in the presence of disturbing forces and moments caused by the various sources. For example, as I told you, in the first stage, wind is the major disturbance, wind as well as atmospheric phase disturbances. Next slide, please. So this is also already I have covered. It is a feedback control problem. Delta input is given and the output is the vehicle attitude measurement and a presence of disturbances. Next. So the controller design. After all these things, the controller has to be designed, which has to have, which should take care of the varying vehicle properties. Like when the propellant is consuming, the mass EG properties will be varying. So each time the vehicle will be different. For that to work, what is the forward and feedback gains required in the rigid body? Rigid body means wherever the total vehicle is acting as a rigid conditions. The 2 points, if you draw a line between the 2 points, during the entire phase of the flight, that the 2 points, the distance between the 2 points will not vary. Flexible means as like a rubber band motion. It won't be like a rubber band motion, but In the flexibility, we will be putting the vehicle in terms of flexible modes, like bending modes, that is coming from the structural data. So with all these things, the controller has to be designed. So it has to take care of varying CG, moment of inertia properties of the vehicle, varying thrust of the vehicle, as well as the bending modes of the vehicle. If it is a stage with the liquid engines and all, liquid engines as well as liquid tanks, then slot properties also has to be considered. So I have covered whatever written. Next slide. So to have an idea, what is the pitch motion, what is the yaw motion and roll motion, it is there. Pitch motion is vehicle up and down motion. Yaw motion is like this. Roll is, as you know, for any vehicle roll. Because in the rocket motion, pitch motion to show it is very difficult. That is why I have put as a aircraft. Next slide. This is the pitch motion and roll motion. Yeah, it cannot show like this. That's why I have put it in the aircraft point of view. Next slide. So this is what I was telling about the bending modes. You can see the vehicle on the leftmost side and the bended diagrams of the vehicle with different modes, first mode, second mode and third mode. This is called flexibility. Slosh is happening for the vehicle which is having liquid tanks, and engine and actuator dynamics also has to be considered in the vehicle model. In the original model, I told you, that model contains all these vehicles, slosh effects, bending mode effects and all. And when you are doing for the design of the GSLV, the first stage vehicle mode, you might have studied, being BTech, sometimes you might have studied about the state space representation of the vehicle, of the system. The order of the system is around 50th order. 50, 52 is the order size when we are designing the controller for the first stage of the GSLV rocket. And next slide. These things I have already covered. Next slide. So things, maybe electronics, they might have studied about the Nyquist plot, I don't know. Because for the analysis, our tool is, the major tool is the Nyquist plot. You might have seen the Bode plot, isn't it? First year itself, first year or second year beginning, you will be studying about the Bode plot. So Nyquist plot is the plot which shows the magnitude and phase with respect to the frequency at any point of time. So all these slot modes or flexible modes are with respect to frequency only. So all our analysis is with respect to the frequency domain. Finally, we will check with the time response analysis with all nonlinearities into the system in place, like dead zone nonlinearity, saturation nonlinearity, that slew rate, what is the vehicle maximum actuator speed it can go to. All nonlinearities will be put in the simulation and we will assess the responses. So next slide. This is the Nyquist plot look like. You can see the bubbles on the right side, and this Nyquist plot is for a PSLV vehicle first stage starting from 0 seconds to 110 seconds. So these bubbles are the bending modes of the vehicle. You can see a small circle with the black. That is the region where it should not go. So that is dictated by the margins like gain margin, phase margin, aero margin, etc. And these modes which you are seeing on the right hand side, that are phase stabilized modes. So I am not addressing about phase stabilization and gain stabilization. First I have put it, but it will not be not relevant to you. Only thing is you have to see that all the modes, vehicle modes in terms of slosh or flexibility has to be stable in flight. For that, what are all things needed a control designer has to do. Next slide. So finally, autopilot design will consist of forward and feedback gains, a time varying gain, and then the integrator to reduce the tracking error, filters to stabilize the flexibility slosh and attenuate the high frequency noise. So all these things has to come in the design, in the autopilot design. Next slide. Here you can see on the left side, left hand side bottom corner, you can see a lag lead to start with. This is a frequency versus magnitude is the top plot, frequency versus phase is the bottom plot. So you can see notch filters, two notch filters that I have marked as 3.56 and 9.3. Those are their frequency, notch frequencies. And the first one, that is the lag lead. Top red plot you can see, it is the time varying forward and feedback gains. And bottom right side corner, you can see a roll of filters. So this is the entire thing will get into the onboard computer for the autopilot. Similarly, for the guidance also, a set of numbers will be there. Next slide. So here I have put a step response to show. Right side you can see. Right side, that red one is an instability bending mode. That is why it is oscillating and going. It is unstable. Whereas you can see the rigid body is stable. So once you have all the filters in place, the correct design, you will have a response like bottom, green. Next slide. So here you can see control structure interactions. So in order to avoid the control structure interaction, one has to design the filters properly. Bottom is the, in the two plots you can see the red ones. Top one is the slosh control interaction. Okay, sir. Then this top one is the control slosh interaction. Bottom one is the control structure interaction. So it is an unstable mode, the red one. In inner you can see a small signal wherein I can see that it is a stable one. If the filter design would have been proper, it will go like a stable behavior. Next slide. Sometimes I may take some 15 minutes more. Is it a problem? Okay. You can see this. Ananda Krishnan? Okay. So you, similarly, this plot also shows a stable one. What I have already I have shown in your Nyquist that the area wherein you should not enter, that black circle, when it enters, the figure will be like this top, that oscillatory red one, which is showing a divergence. When your design is paka, like a blue circle, the behavior will be like this. What is the problem with divergence? Like a divergence means it will go to a higher angle of attack, and Q alpha, it is a measure of the strength of the vehicle, will increase and the vehicle will break. That is the one which is showing that flexible control structure interaction has to be avoided. Next slide, please. So once you design the trajectory, guidance, and control, we will have the total 6D simulations. So there are some offline simulations and some are real-time simulations. Real-time means it has to have the same time. Suppose it is a 15 minutes flight, the real time also will take 15 minutes to run. Whereas offline simulation means we can have n number of simulations in offline. So all our studies like Monte Carlo, everything will be in offline. When you have all onboard computer in loop, you have to have real-time simulations. That is why I have put OILS, OBC in loop simulations, HLS, hardware in loop simulation, wherein the actual sensors except the accelerometers will be there. Then the performance oils and actuator in loop simulations. Next slide. What is a 6D trajectory simulation? Once the mission specification is finalized, we do the mission design for the above specification. Yeah, sir is telling that opportunities for fresh engineers, that after the presentation I will touch upon. So building the system and conducting the experiments for each of these are costly, and we will go for a trajectory. Yeah, sir is telling that sir is going because of the, okay. Okay then. Thank you, sir. Okay, so this is the trajectory simulation. Next slide. I'll be going fast. So once the NGC design is over,
Sorry, madam. You can take your own time. Because of the other meeting only I am going. Otherwise, I would have continued till the end. There is no hurry.
okay, sir.
It's
Okay.
important for the students.
Okay, sir. Thank you. Thank you, sir.
All the best. I loved your presentation. Thank you.
Okay, sir. So trajectory design is there, CLG design I have told, DAP design, and then goes to the 6D simulation. So all these terms designs will turn into a set of numbers and a program. This program as well as the number. The numbers is called the init data or the initialization data, which goes into the computer. The program also is also in the onboard computer. Once you are from the ground, when it lifts off, everything is taken care by the onboard computer. So this is the NGC design in a nutshell. So it is sometimes it may be an iterative process also. Next slide. Next slide, please. Okay. So this Monte Carlo analysis, because our design we used to do with all variations in the +3 sigma side or -3 sigma side. Sometimes the mission is not achievable, to be frank, with the cost-effective things and all. Then we will go for a Monte Carlo, even otherwise, Monte Carlo analysis we will go. So all these parameters, something like some hundreds of parameters will be varying within the allowable limits. And then we will do n number of simulations, like thousands of simulations or 2000s of simulations, and we assess the degree of result going into the orbit. Suppose one case in thousands or 2000 is not meeting the orbit, we cannot say that the mission will not survive. That particular case alone we will analyze, and suppose that case shows a separation disturbance of 10 degree per second, and we will know that such 10 degree per second will not come into flight. With that scenario, we will clear the flight. So that is the importance of Monte Carlo simulations. Next slide. So this already I told, there will be n number of parameters which will be varying in flight. All these parameters will be varied in the Monte Carlo sense, like random numbers are generated for each of the parameters, and a specific set is generated. For that specific set, we will run the simulation. Simulation means all our design numbers, vehicle model, actuator model, sensor model, everything will be there with the disturbances expected, wind, atmospheric disturbances, and then we will have the analysis, whether it goes to the orbit, whether the separation is clean, what is the rate maximum experience, all those things will be analyzed. Next slide. So this is the identifying the distribution of the input variable, random generation, and a sample generation, and finally the error estimation. Next slide. So you can see what is the one simple parameter I have put, what is the variation with respect to the inert weight of PS1, PS2, PS3 and PS4. PS1 is nothing but first stage, PS2 is PS2 and above, PS3 is PS3 and above, PS4 is the fourth stage. So in the MC sense, all the parameters are varied, and we will find out the probability of the output, orbits, orbital dispersions, etc. Next slide. So this also I have covered, like architecture of a single MC run. In each run, the set of outputs are stored, and these stored outputs are analyzed statistically by considering each run as a sample, and probability of occurrence of extreme events like impact point violation, end depletion, etc. also has to be analyzed. You can see the right side also, MC simulator output. At separation, what are the conditions? Everything is marked, all Arctic. Next. Next. Okay, this also shows that bottom is the one where you can see the blue one is impact point of that stage for each run, and that red one is the area which you should not enter. So you can see all our impact is inside the allowable zone only. Next slide. So this wind biasing technique which we are using in the first stage, that means because if you are in a position to go against the wind, then you will be in trouble. That alpha tracking error will increase, Q alpha will increase. So what we will do is, for such small time, we will go along with the wind with some penalty on the velocity. When you are going along with the wind, you will not be in an optimal condition. Satisfying that condition, we will do that because the vehicle stability is important. For that, we will use the wind biasing technique like mean wind biasing on the at DSLV, PSLE initially, and then we went to day of the launch wind biasing. On the day when we are launching, we will measure the wind like T minus 2.5 hours before by sending the balloons and get the wind data and get the trajectory for the first stage for the wind, designed wind, and then that portion of the trajectory, that theta is IC, will be merged with the upper stage trajectory. Upper stage will not change. That is what I call it as a day of the launch wind biasing. You can see the winds are changing in the two fashion, in the zonal and meridional. That black one is the mean wind of that month. On the day, the winds are very much different from the mean winds. So if you are going with the mean wind biasing, it won't work. So that is why we are going for the day of the launch wind biasing. Next slide. Next slide, please. Yeah, this also you can skip. And these are the balloons we will raise on the day, and get the information, and the final data, trajectory data, is loaded T minus 1 hour, and then T minus 45 minutes the init will be loaded. Before that, you have to consider the wind on the day and simulate all kinds, including the Monte Carlo analysis, and ensure that the orbital conditions are met and vehicle stability and integrity is ensured. Next slide. And this is also what are the balloon races and all. It's not required. You can go to next slide. Yeah, here I have put a video of the Chandrayaan mission, I think. You can run the video. Is it working? No. Down you can put an arrow mark. Yeah. Maybe system dependent. Maybe it is taking from my system only. You can double click. Yeah, no problem. It is a video available in net only, no issue. Chandrayaan video I have put. So this covers my presentation in the sense that if you are in a position to do the design aspects, how do you design a launch vehicle? What are the important points to be considered? In what are all areas you should have expertise. So with respect to sir's request, I will put like this: the opportunities in the ISRO. For example, if you are a BTech engineering graduate with respect to electrical or electronics or computer science or mechanical or any graduate from a recognized university, no doubt CET or our colleges in Trivandrum, no issue. Only thing is, if you have a passion to reach to VSSC or ISRO, you have to be, you should not be studying for the exams, that in and out of each one you should know. For example, our interviews, once you clear the test itself will be like your gate exam and all. Once you clear the test, you have to go for the interview. To be frank, interview is very tough. They will ask only the fundamentals. So every time when you study or write an exam or write an assignment or prepare for a presentation, you do it with passion. I don't know whether sir is expecting this kind of words from me. I don't know. But what I have seen is, even from IITs, some candidates are coming. When we are asking that simple questions, they will not answer. They will be knowing that big things. But for the graduation level onwards, you should study with the passion all the subjects, not only of subjects of interest. So that is the request I have to give. So if you are good in studies, you will get a very good mark also, no doubt. So some cutoff marks will be there for the entrance. So mark also matters. After the getting the marks, you will be called for the test. Then the test you have to go through, and then the interview. So only thing is, again it comes to the point that when you are studying, study with passion, study with the, not for the exams or for the marks. Everything should be known to you when an interviewer asks. That is one part. And with the BTech, you will be able to get engineer SC post. And if you have a passion to go to MTech, continue in MTech in reputed colleges, CET or any college. There also you have to have that mark level limit. Sometimes MTech will be having interviews. So the opportunities are there for all BTech engineering graduates, whatever may be your stream. BTech mechanical is there, computer science, applied electronics, EEE, whatever may be. So you have to you have to go through our website, ISRO website. It will be called, and I think 99% on merit only the selection is. So this much only I have to tell about the selection part and opportunity part of, not only in VSSC, you can have URSC. So many challenging opportunities are there for ISRO in space. And one more thing I'll tell. Nowadays, so many startups are there in space. And I am also Director Control System for Skyroot Aerospace. I'm doing in online only, but all their meetings are in Teams. So such a problem I have not faced and I have not presented. But which forum I don't know. Okay. So startup opportunities are also there. Space lab is there. Our Sheila madam is having a space lab. So enough opportunities in the space area is available to you. Agnicool is there. Some 250 engineers are there in Skyroot. So for engineering graduates, enough opportunities are there, not like our time. Bindu and all may be knowing. And nowadays, you see, my mother used to tell a doctor is always, recognition is there, no doubt. And after retirement also, they will be getting earning member. Now I can say that engineer is also an earning member after retirement also. So all the best to all of you, and try to get a job in space area. It is a challenging area for all of you. Every time you can study, it will not be boring at all, because every day, even after retirement also I am studying. So it is a good opportunity to all of you to reach to space area, either in government sector or in the private sector. I think I have covered all the best. The time also is around 9:20. I have to finish it off by 9. Any questions are there? You can ask now, or through my mail you can ask. If I am able to answer it, I will do it. Otherwise, I'll get the help of my juniors there and all, and I'll give you all the required or satisfactory answer. Thank you. Thank you so much for IEEE, and extremely sorry to delay for 20 minutes. Thank you all.
Thank you, ma'am, for sharing your knowledge and experience with us. Before we get into Q&A session, let's take a virtual photograph to capture this moment. I would like to request all to turn on your cameras and bring a beautiful smile to us. And Anjal, can you do the honors of clicking the picture for us?
Yeah. Bindu is there. Bindu is not seen.
Madam, you have not switched on the camera, I feel.
Yeah, I am
Have you?
seeing. Yeah, maybe your tiles different.
Maybe. Maybe yes. Maybe.
Chaitanya, you are seeing me.
Yes,
Yeah,
ma'am,
ma'am.
I can see your
Okay, so
camera is switched on.
Maybe another tile.
Maybe so. I'm using my phone.
Yes, ma'am, I'm going to click on the count of 3, 2, 1, smile. Okay, thank you.
Okay. Then.
Thank
Actually,
you, everyone.
madam, just to supplement what you said, madam, like when did cricket become a craze to India? After we won the World Cup, like
Yeah.
we find that India can make a mark in the area of cricket. Similarly, now the craze is on spaces or space and space related job also, because now we have proved that we can make a global mark in the area of space by showing the Mangalyaan or what and the Aditya L1, etc. So, as you rightly pointed out, now we have the youngsters have lots of options in which we can show our might. So, as you rightfully said, I also would like to tell them, you just do your hard work, and then the world is yours. Not only the planet Earth, but moon and universe is yours.
Yes, and so many challenging opportunities are there.
Yes, ma'am. Yes.
So I am requesting all of you, in which year I don't know, after completing BTech, join in VSSC or any of the centers of ISRO. All the best to all of you.
Thank you, ma'am. Our feedback form will be shared in the chat box. The certificates will be distributed based on it, so kindly remember to fill up this form. Now let's move on to the Q&A session. If you have any queries regarding the topic, or if you have anything in general to ask the speaker, you feel free to unmute yourself and ask the question, or you may also put that question in the chat box.
Somebody can read the question. I am not able to see anything here. In between, I was correcting my throat. It was not well for the last 10 days.
Ma'am, I think nobody has any questions, so I hope that everything is clear to you. Okay, Anju Maria.
You can send the questions to mail also. If you are reluctant to ask now, you can send. I will answer it.
Anju Maria, either you can just type or just unmute.
Ma'am, in the meantime, I have a question for you. Ma'am, for a person who wishes to join VSSC or ISRO, will it be better for him to join directly after BTech, or will it be better for him to continue his education first, as in to pursue MTech or PhD and then join VSSC? Which will be better?
If you ask me, I will tell, if you are in a position to have MTech with a higher score, and like if you are getting a job, getting IIT MTech, then it will be good. But what I feel is, if you are in a position to reach after your BTech, it will be good, because from there also they will send you to take MTech or PhD. That is one part. I'm not telling that you should not go for higher studies. The opportunities will be high if you are going with the BTech. In the sense, the number of vacancies will be very high. After MTech, you will have only 2-3 vacancies. So you have to fit the requirement what they are projecting for you. So in that aspect, better try for just after BTech. And if you are passionate to for higher studies, they will send you with the government money. They will send you to higher studies in IITs, IASC, and sometimes outside India also. But that money you may have to pay. Only the leave they will give. That is the present strategy. Sometimes the strategies can change also. Are you okay with my answer?
Yes, ma'am. So is it as in the student can continue with this job and at the same time pursue higher studies? Is it like that, ma'am?
Yes, yes, yes.
Oh,
Sometimes if you are going, I have with me some very good colleagues that they have joined after BTech. So I also told them purposefully, you can take a leave after 4 or 5 years, and they went for integrated MTech PhD. They went for integrated MTech and PhD, and they got PhD now. But somewhere you have to have a loss of 1 year or so in the promotion that you have to live with. എല്ലാം കൂടെ നമുക്ക് നടക്കില്ലല്ലോ. So in that aspect, you have to say 1 year loss is there. That is not a, after 30. Even I have 33 years of service. Even I joined in 27 years. So a person joining in 22 and all, they have 38 years of service. So in that 1 year loss and all, you need not bother. So that's the one.
okay, ma'am. I have one more question. I hope that is okay. Ma'am, I believe there are some institutions that offer courses that is related to space science, such as the Indian Institute of Space Science and Technology, the Indian Institute of Astrophysics in Bangalore. So, do you think pursuing undergraduate or graduate studies in such institutions will be beneficial while joining VSSC or ISRO?
Definitely answer has to be beneficial, but which stream you are taking? Suppose you are taking an atmospheric studies as your elective and all, you will be fit for that area, like space physics laboratory and all. So to be frank, for graduation, take electronics, mechanical, electrical and electronics, like broad area you take. When you go for MTech, you can have small specialization. And otherwise, that the organization should give you a guarantee they will accommodate. I'm not very sure about these things. You can also check up with their website and all, whether they will accommodate after your graduation and all.
Oh, okay, thank you so much, ma'am.
Does anyone else have any other questions?
Ma'am, can you tell what are the opportunities available for computer science students at ISRO?
Oh, very big opportunities are there. Whatever I have presented to you, that onboard computer, it is by the computer engineers. The onboard development, onboard software development, a big team is there. Software, on the software area, as well as on the hardware also, it is there. So computer engineers, Not only the maintaining computer, one department is there maintaining computer facilities to all our employees. That is one area. Another area is you can work on the flight computer itself. Enough scope is there. Not only in VSSC, URSC is there. All centers are there.
Okay, ma'am.
Mechanical engineers are there, electronics engineers are there. So many. When I retired as program director of space transportation system, wherein I have all mechanical engineers, electronics engineers, electrical engineers, computer engineers, all streams were there. But as I told you, that fundamentals you should know and you should study with passion.
Okay, ma'am.
Any other questions?
I think we can proceed. I
Yeah,
hope
I
all your queries have been answered. Now, as a token of appreciation from our side, we would like to present Dr. S. Geetha with a virtual memento. For that, I would like to invite Anjal to share the screen and present the virtual memento. Now, let's move on to the
Thank
vote of
you.
thanks.
I should thank Bindu also. Initially, because of this problem, I forgot. I thank IEEE Education Society, as well as special thanks to Bindu. Thanks, Bindu.
Oh, no. My pleasure, madam. Just, many of these students have not yet come to know much about these aspects of the mission, especially very much important in these days. So I'm so happy that you came and presented. Thank you very much.
Thank you.
Ma'am, it is our pleasure also to have you on board. Now, let's move on to the vote of thanks. For that, let's welcome Mr. Vyasan J, Membership Development Chair at IEEE Education Society, Kerala chapter. Over to you, sir.
Okay. On behalf of IEEE Education Society Kerala chapter, I would like to express our sincere gratitude to Dr. S. Geetha for an insightful and engaging presentation on launch vehicle mission design and challenges. The challenges she highlighted were informative, sparkled curiosity, and encouraged further explorations. Her passion for the space industry and her dedication to knowledge sharing were truly inspiring. The knowledge gained from this session will benefit all other attendees, encouraging them to ask further questions and pursue technical professional interest. We would like to thank all of you, the attendees, for joining us for the first episode of Pro Talks. Your participation and questions makes these sessions truly valuable. Once again, a big thank you to ma'am for taking the time to share her expertise with us. We look forward to see you all on the next Pro Talk session. Thank you, everyone.
Thank you all.
With that, we have come to the end of our session. Hope you all had a great time. Don't forget to fill out the feedback form, which is posted in the chat box to get your certificates. Once again, thank you all for actively participating in this event and making it a great success. We will look forward to seeing you in our future sessions.
Thank you. And all the best to Education Society for further thoughts. Thanks.
Thank you, ma'am.
Thank you, madam.
Yeah. Shall I leave?
Yes, madam. Thank you.
Yes, sir.
Okay.
Thank you, ma'am.
Thank you.
Thank you.